my Michaela off to UC Santa Barbara this weekend. It was crazy. I was kind of fine. I was pretty much fine there, just setting up the room. And then we got home and I saw like her little tuft of hair in the bathroom, or like her towel. I'm like, oh, we could put that away. She's not going to use that. It's sad, but it's good. Moving on to bigger and better things. So intro, chapter 2, reactivity. And again, look through these outlines. They're good. Keep you up to date on things. I got Jason Giuliani. I don't know if any of you had him for general chem. My daughter, Michaela, wants to study biochem. She wants to be a radiologist maybe at this point. We'll see. And so this email, I got an email from Jason Giuliani. He's a chemistry teacher here. You might have him at NCC, the Nevada County campus of Sierra College. So there's this job, lab technician job. It could be part-time. If you're interested, you're doing like water sample testing, I think. Looks like they do well drilling. So they got to check to make sure if you get water from the well, it's clean and safe. So if you're interested, let me know and I'll forward you the email with the details. Looks like a good opportunity for those who want to get some lab experience. And yep, let me know and I'll forward you the email. And then, so tell me about yourself for extra credit. I haven't gotten any of these yet. I don't know why, because it's just easy 1-point assignment. So let me know about yourself, get extra credit. And you can use the IR and the NMR before labs. I've mentioned this before, but again, you can do that. And my office hours, I'd like you to come more. So this is a repeat. So come to the office hours. I got some new one since I posted this last week, but not many. So come on down. It is the week of the first exam, so I'll probably get more people. And then make sure, what did I hit a link, sorry. Work on your coupling predictions. Those are some of the more challenging things. So I got the monosubstituted benzene prediction stuff here. Exam, oh, it's not next week, it's this week, huh? That's from last time. Exam 1 this week. So, oh, I'm sorry, I got sidetracked. Oh, so I see comments about office hours. If you can't make my office hour, you can ask me some questions sometimes in lab, especially now that we're getting through with the training. I should have more free time to, like, if you have a little side quick question. And then also take advantage of Morgan and his past peer sessions. So his past peer sessions are Monday, Wednesday, 9 to noon, I think. And then my office hours, Tuesday, Thursday, 9 to 10. All right, so exam 1. I have a question about my office hours. Do I record them? I don't record them video-wise, but I do post the Jamboards with all the questions we work through, and they're a great resource to go through. Okay, so exam 1, I'll try to write an exam that should take the average student about an hour and a half. I mentioned this before, but yeah. So you have more than enough time in lab, I believe. But you can still come early if you like. And if you want, on Wednesday, you come at 1 p.m. instead of 2 p.m. normal lab start time, or Thursday at 9:45 instead of 10:45, the normal start time. And then Thursday lab people who start at 2 p.m., you can come at 1 p.m., basically an hour early. And you'll just put your cell phone up front. I'll give you scratch paper in the exam. We'll get it done. The material will be, chapters 1 and 2, outcomes here. Some key topics: bond line structures, formal charge octets, of course, curved arrow mechanisms using colors for the reacting electrons. So if you have colored pens or pencils, bring them. If you don't, I have some you can borrow. And then hybridization and the sigma bonding diagram. This one, I made the exam this weekend. We're driving on the 5 and the 101. Well, my wife was driving. I was trying to write. And then it was sometimes I'd get to points where I had no sight. I'm like, I gotta pause. But so I wrote up the exam, and I think the sigma and pi bonding diagram, that one takes me the longest because it's like, it seems like it always grows a lot more than you want it to, the sigma bonding. Actually, if you want, I think it might be easier to do the pi bonding diagram before the sigma bonding diagram on these type of problems, but definitely practice that. And then, Aline's got that cool structure and I like it. And then reaction coordinate diagram, I think that's going to be our biggest point problem on the exam. So practice those, and I'm gonna actually do another one today. pKa, use pKa to protect acid-base reactions. Yeah, no, there'll be a quiz on that today and tomorrow as well. And then alkane nomenclature, I'll do that today. And then the spectroscopy multiple spectrum problem. We did an example of that last week, and there's a bunch of them in the NMR and IR workshop. And the NMR and IR workshop was due Friday, but turned into me today and tomorrow to avoid late points. And determining unknown structures with NMR and IR, that's not due for a while because we have to let everyone get a chance on the NMR. Solubility of organic compounds. So I have a minimum of all the questions answered up to the point where you are asked to perform wet chemistry. I'm hoping everybody's already there. I was hoping that should have been like last week. So that's up to question 14. And then when you come into lab, you can start doing the experiments, and you can go ahead too. If you've got time, you can like skip over the wet chemistry parts and go to the intro to the next section. And we do have the pK and acid-base reaction equilibrium quizzes today and tomorrow in lab. So check those out. I think I have 3 or 4 quizzes in there, and then you'll get one of them. And I'm updating the experiment crystallization of organic compounds. That'll be the next one we start after solubility of organic compounds. You can look at it if you want early. That's the link to it. And oh, I didn't set this up well, but okay. Homework A is late now, but if you turn it in by tomorrow, it won't result in any late points. So get that in by tomorrow so you don't have to lose points. And the due dates and how late you can things turn in are all on this Google Sheet. And then homework B, I posted that over the weekend. I finished it up, and that's in Canvas assignments is linked there. It's also in the organic step-by-step, and it's in the due dates sheet. So lots of ways to find it. And the key, keys for a lot of the things we do. For example, let me go into this. I have a key for, this is from last year. I had chapters 1 and 2 as one homework assignment, but this year I separated it. I added to the chapter 1 stuff, so I separated it out. So, but your homework 1 and 2 keys, like your answers, most all of them can be found in here. So look there, and then homework B, chapter 2. Oh yeah, I'm just kind of telling you, look above. That's where you find it for homework B. Oh yeah, and this is, I should call this something different because this is not homework. Homework, I'll just say chapter 2 and 3 and 4 key. Okay, so you can find some help there. So feel free to come to lab early today to run NMR, even if you're a Tuesday, Thursday lab student. You can come, if you're on campus, come on in, run the NMR. Say from about 1 to 2. I'll be in my office, like getting the lecture video finalized and uploaded, doing other stuff, and you can be in there. I can be helping you. And if you're a DSPS student, please let me know if you'll be taking the exam in lab or at the testing center. I sent an email out, so check your school email about that, so I know what to do with that. Okay, any questions? Oh, actually, I had one more. Huh? Does anybody want to come in early for the NMR today? If you do, come on back. So any questions about the intro? Could we do, after we finish the test, do we leave or are we working on other stuff? I think, good question, after you finish the test. I'd like you to stay and work on other stuff, but we'll see. It'd be good for you to stay and like run the NMR or something like that after the exam. And then someone asked, could we do a little review of sigma pi bonding diagram? I don't know if I have time for that right now, but ask me first. You know, I made a exit question a while back, and then why don't you try that? We'll see. Then you can show me your answer. And then does homework B have exam content questions on it? Homework B. Yes, it does. Yep. It's got some, whatever the topics I listed above, chapter 2 stuff. All right. So I think I said that actually at the very beginning. Did I say that at the beginning of the homework stuff? Yeah. So outcomes, exam material for the exam will be chapters 1 and 2. So homework A is chapter 1 and homework chapter 2, that's homework B. So, and these are the outcomes. So there you go. So not everything on B will be on the first exam. Some of it will be on exam 2, but you definitely want to look at homework B to like get yourself some practice at stuff that's going to be on the exam. So let's go to my lecture, my chapter outline, outcomes. Chapter 2. Start by reviewing pKs and then compare and contrast thermokinetics. Okay. All right. So let's review the pK stuff. I said that was going to be a quiz today, right? Let's do a quick review of pK stuff. Okay, so sulfuric acid, what's its pK? -10, good. I see a lot of -10s on the thread, good. I see 110, make sure it's not 10, it's -10, because it's gotta be negative, it's strong acid. And then hydrochloric acid, what's the pK? -7, good job. And then hydronium, -2, -1.7 or -2. And a carboxylic acid, like acetic acid. About 5, yep. Not -4.7, but it has to be, that's a positive one, it's a weak acid. And then ammonium, 9.2 to be more precise, but 9 is close enough. And then an alcohol like a methanol or water, what's their pK? About 16, yep. Good. Then ammonia, the nitrogen without the positive charge and a lone pair, about 35. And then methane and alkane, about 50. Okay, so we got those reviewed. Let's do some quick examples of this. Gotta find my lecture outline, or no, my Jamboard for today. So here it is. Okay, let's think of an acid, maybe let's go with an alcohol. Yeah, let's do an alcohol. How many carbons do you want in the alcohol? Maybe like between 5 and 10. What number of carbons do you want? Okay, we'll go 4. I saw 4 first. 1, 2, 3. Yeah, we'll do this one. This is a T-butanol. Okay. So here we go. And then let's make, we'll make that, actually, yeah, I'm gonna do this different. Sorry. And I'm making a carboxylic acid on this side. How many carbons do you want for that carboxylic acid? Over 5, how many? Oh, I got a 7 up there. 1, 2, 3, 4, 5, 6, 7. Let's see, 1, 2, 3, 4, 5, 6, 7. Yeah, okay, we got a nice long one. So we got these 2 molecules. which one will act as the acid and which one will act as the base? So the carboxylic acid, what's its pKa? About 5. And then the alcohol, what's its pKa? About 16. So I'm going to say the acid's much stronger than it's going to be the acid. So I'll call this my reactant side acid. Good. And then let's do some reacting. The alcohol deprotonates that hydrogen, breaks the bond, and we get what am I doing? I got confused. Having to use the colors really slows you down. It makes you think about it more. I think it's a real positive thing. Okay, got my acetate here. Not my acetate, my carboxylate. And let me double check my numbering. 1, 2, 3, 4, 5, 6, 7. Looking good. And this has resonance too. Let's go ahead and draw that. We'll practice our resonance. Oh, here I wasn't touching. We should be touching. We're always touching. There we go. At a safe distance with our masks on. There we go. There we go. Nice resonance structure there. Stabilizes this base. Okay, so I've got my reactant side acid here. That's the reactant side acid. And then on the product side, what would be the acid if I reverse the reaction? Is it going to be the protonated alcohol here? Is that going to be the product side acid, or is it going to be this carboxylate? And imagine the reaction going like this, boop, to reverse it. Which one's donating a proton? What's the Bronsted acid? And which one's receiving the proton, the Bronsted base? This is your product side acid. Oh, sorry. This is your product side acid, right? Good. All right, so what is the pKa of that product side acid? What's it look like? And oxygen, let me not put that. 3 bonds, a lone pair, and a plus charge. What is that looking like? Looks like hydronium, right? Yeah, so the pKa of this product side acid will approximate about -2. Okay, what's the stronger acid? An acid with the pKa of -2 on the product side, or the acid with the pKa of 5 on the reactant side? Stronger acid. Yep, that's the stronger acid. So if that's the stronger acid, then is this a reactant favored reaction or a product favored reaction? The strong acid's going to push the reaction towards the reactant side. reactant favored. Reactant favored. Okay, and then finally we'll do the K equilibrium calculation to see how reactant favored it is, and yeah, the magnitude of it. So the equation is 10 to the product side acid pKa minus reactant side acid pKa. So that's going to be 10 to the product side pKa is -2 minus the reactant side acid pKa is 5. It's going to be 10 to the -7. So yeah, reactant favored. There's going to be like 10 to the 7. That's 10 million, right? There'll be about 10 million reactants to every one product. Very, very reactant favored. Okay, so I'm going to do one more of these because I want to tell you one of my tricks. Do you guys want one of my tricks for exams? So for exams, I like to write questions that make you think a little, and they have like everything, all the concepts I've taught you. If you know them well, you can get the problem. But if you don't, then you're going to be in trouble. Like it's not going to be, the exact same answer. Every question is not going to be the exact same kind of question I've asked before, where you can just memorize it. So I like to make you think a little bit about it, and I like to feel like my exams are fair but challenging that way. Like I feel like most of my students in the past haven't said like, "Oh, that question came out of left field. You never talked about that." I don't like that kind of question, but I do like to still have them challenging. So, like for example, one of the ways I like to do that is I like intramolecular reactions. So intramolecular reactions are reactions in which a molecule reacts with itself. So let's look at an example of that. Let's do one with I'm gonna try a cool one. Let's go, I'm gonna put like a sulfuric acid type derivative over here. I thought about doing a question like this on the exam, but I didn't. But I was like, I thought about having a question with like a sulfuric acid derivative like this. And I was like, oh, cool. I'm surprised I haven't thought of this before. But then I thought, no, it's kind of maybe too much. Let's see though, if you like this, let's go. Okay, here it is. Let's see, what is this going to be? 1, 2, 3, 4, 5. You know what? I like 6 better. Let me fix that. Okay, so if you look at this, what does this side look like? What does this look like? Sulfuric acid. Yeah, and what's its pKa? -10. Cool, and then what's the acid on this side? The alcohol, what's its, not acid, what's the pKa of that one? It's about 16, yeah. Okay, cool. So who's gonna act as the acid here? The alcohol is the weaker acid. So can you see how it can reach around and do an intramolecular reaction, reacting with itself? Isn't that cool? Oops, the oxygen. Okay. So yeah, the intramolecular reaction. So the other type of reaction, intra, you react with yourself. Inter is two molecules reacting. Okay, so this one's intra, sorry. Like last example. All right, so is this product favored or reactant favored? What do you think? So what's the acid on the reactant side? Is it the sulfuric acid derivative or the alcohol? What's the acid? The sulfuric acid derivative, huh? This is the reactant side acid. And then if we reverse the reaction, that means the sulfate would have to reach over and deprotonate this guy. So this is your product side acid. So the sulfuric acid, the reactant side acid's pKa, we already said is -10. What about the product side acid's pKa? It's about -2. So what's the stronger acid? Stronger acid. So this is a reactant or product favored reaction. Strong acid's going to push it to the product side. Products. Reaction. Yeah, and then the K equilibrium. I see some of you already calculating. I like it. K equilibrium is 10 to the product side acid, which is -2. Minus, this one can be tricky. It's got a minus, so minus the -10. So that's 10 to the -2 plus 10. This is 10 to the 8, very product favored. There we go. So do you like the intramolecular? Kind of just makes it feel like it's a little bit different, but if you're following the same concepts, it works. All right. Now, that exact problem won't be on the exam, but something like that might be on the exam. Okay, so start by reviewing pKs and compare. Oh, thermodynamics and kinetics. So let's do a quick review on this. Oops. So thermodynamics and kinetics. So thermodynamics is looking at just like the reactants and products, just nothing in between. And kinetics is looking in between. So it's just trying to describe how the reaction takes place between reactants and products. And we're Annalise, we did one reaction coordinate diagram last exam, but then we're going to do another one now too. Are Lewis structures of Lewis acid base molecules on the exam? Lewis structures can be on the exam, acid base can be on the exam. So yeah, I'm not you kind of mixed two things there, Santos. But all right, so now thermodynamics and kinetics. So nothing. So if you look at like K equilibrium, what do you think? Does that seem like it's a thermodynamic quantity or a kinetic quantity? So K equilibrium is the concentration of the products. You have to know about the products, and you have to know about the concentration of the reactants. You have to know about the reactants. So which one does that go under, do you think? Kinetics or thermodynamics? K equilibrium's kinetics. I mean, thermodynamics. What about pKa? Kinetics or thermodynamics? Thermodynamics. Because pKa is negative log of a K equilibrium, the K. And then what about pH? pH of a solution. It's asking about the concentration of hydronium product. So it's over here too. What about a rate constant, like the rate of a reaction? Sorry. Let's just say rate, the rate of a reaction. That sound like kinetics or thermodynamics? Thermodynamics. Because rates, it is dependent on the concentrations, but it's this guy. It's telling us how fast it reacts, talking about in between reactants and products, how fast that's going to happen. Okay, and then what about activation energy? The energy it takes for two molecules to react, they need to collide, and they have to collide with enough energy to overcome the highest energy point before they become products. That's kinetic. That's a kinetics. And then what about transition states? Transition states kinetics too. Because it's talking about between the reactants products. All right, and then this is more. The change in enthalpy, delta, or tell the delta G, say the change in Gibbs free energy, delta G, where's that gonna go? Thermodynamics. Because the delta G is based on the energy of the reactants and the energy of the products, energy of the reactants. And then delta H, same thing, a change in enthalpy, change in entropy, those are all thermodynamics. I'm trying to think what else is in kinetics. Oh, the mechanism, what about the mechanism of the reaction? We do curved arrow mechanisms, that you can kind of consider that as being like kinetics. Okay, so we got the idea. When I learned this, I remember it took me a while to understand this, but now it makes sense. Thermodynamics is considered a state function. It just depends on the state of the reactants and the products. And a kinetics is a path function. It's understanding the pathway between reactants and products. So I'll write that up. State function. Path function. And there's math involved with this stuff. You remember these things like delta G equals delta H minus T delta S, all that stuff, but we're not going to really do much of that math. We're going to learn it. We're going to talk more about it qualitatively than quantitatively, even though that math's not that hard. I mean, there are parts of it that are. Okay. So yeah, I think you'll like this. I think there's a lot of things in OChem that make you understand general chem a little better, and you actually will like it more. Okay, so we got those. Yeah, I think we've had everything, right? So now reaction coordinate diagram. So let's do another energy versus reaction coordinate diagram, because that'll be on the exam and it's going to be a big point problem. Take you a little while. Let's make sure you're good at it. Energy versus reaction. I wanted to make a Google slide animation of this. That's the next one I need to make, but I just didn't. I had to write the exam first and then the exam key, because you write the key, you find all your errors. So yeah, I haven't got a GSA for you on this one yet, but we'll get you one soon. Okay, so let's do this. Let's go. I'll show you the overall reaction and then a curved arrow mechanism for it. Overall reaction first. Okay, so let's do, I'm gonna do what's called a Sn1 mechanism. This is how it works. I'll start with something we're gonna learn later is called a electrophile. This is an electrophile. I'm just throwing this word out there just so you hear it. And our nucleophile, I'm gonna go with methanol. And then I'm gonna cool this reaction to favor what's called the Sn1 reaction. So this is the overall product of this reaction, products. There we go. So does it look like I have a balanced equation here? Do I have atoms balanced? Let's see. I've got like this 4-carbon unit here, 4-carbon unit. I got a methyl. Oh, I guess to be fully balanced, I should say there's like 2 of those, huh? And then, yeah, so I've got the other version of that. And then, yeah, looks good. I have 1 hydrogen, I have 2 now because there's 2 of them. And my bromide, there we go. And then maybe even more important one for us is to make sure the charge is balanced. So what's the charge on this bromide? 0 charge, the methanol 0. Overall, I got 0, -1, +1. Oh, adds up to overall 0. Looks good, charge is balanced. So let's do the mechanism. This mechanism starts off pretty weird. The leaving group just pops off on its own. So on the exam, I wouldn't expect you to know this mechanism by heart, but I would expect you to be able to, like, say, add the missing products if I gave you the curved arrow mechanism, or to add curved arrow mechanisms if I just gave you the products. Okay, this is the first step of this mechanism. And can you see how the curved arrow mechanism should work for this? The curved arrow mechanism for this one's easy. It's just the bromide leaves on its own. So those 2 blue electrons become a lone pair on the bromide. And it's kind of weird because the molecule is just kind of ripping itself apart. But this can happen. This is an intramolecular reaction, right? The molecule is reacting with itself. And this particular reaction, all that's happening is a bond is broken. So if I only have a bond breaking, does that take energy to break bonds, or does it release energy when you break bonds? Yep. Little side note over here. Takes energy to break bonds and releases energy. When bonds break, form. Okay. So we said that earlier quickly before, but now we're going to see a little more. All right, so is this reaction to go from reactants to products, does it take energy or does it release energy, do you think? Takes energy, yes. So this reaction, this first step is it takes energy. This step is, it's a exothermic or endothermic? It's an exothermic step. Oh, what am I thinking? Thank you. Endothermic takes energy. Endo. Okay, so now there's another thing about this one. This is also the rate determining step. This means it's the slowest step in the reaction. And so it determines the rate of the whole overall mechanism. Okay, so next step, that's the first step. Second step is this, what's called a carbocation. Has a water molecule come over to it and bond to it. Actually, I'll leave that. Oops. This water molecule is going to come over and it's going to bond to the carbon that's missing a bond. That carbon doesn't have an octet currently, huh? It's got 2, 4, 6, no octet, wants to have another bond. So water will come along and add to it. And I'll get the following. Oh. Okay, so that carbon no longer has a plus charge because it gained a bond. It's got 2, 4, 6, 8. It's got an octet now. It's in group 4, minus 1, 2, 3, 4 bonds and no electrons. Looks good. Okay, so this step is, it involves a bond being made, right? Are any bonds broken in this step? So it's this one, the bond is being made, and bond making bonds releases energy. No bonds are broken. So this guy is bond made, none broken. This step releases energy. So it's exothermic. Okay. Next step. Oh, I had a question about, I said the rate determining step determines the rate of the reaction for the overall reaction. So this slow step is what's going to determine how fast things go. This next step is really fast. So it's just waiting on this first slow step. And then once you get some of this, boom, this happens quickly. So the reaction is the overall final products are dependent on just this step. That's the slow step. The rate determining step. Okay, next up, the product here with the protonated alcohol. Oh, you know what I did? Whew, I made a mistake here, didn't I? Anybody notice? I'm way off. I'm using water, not methanol. Sorry about that. Typo. Okay, so I've got this protonated ether. This is going to get deprotonated by another methanol. And if you have the overall reaction, you can see, oh yeah, it looks like that did happen. There it is, right? So this is going to reach over and deprotonate that. And we'll have our final product. Oops. Actually, I made this bond. I made this curved arrow green. I should make that black, huh? All right, there we go. And then this will look like so. Okay, got it. And I had a question about, should you know that this is the rate determining step? No, not right now. You wouldn't know that was a rate determining step. It would be given to you. And this last step. So we have a bond broken here. This bond's breaking. That's going to take some energy. And we have a bond forming. This is the bond forming. It's this one. That's going to release energy. So what's your guess? Do you think it's going to take more energy to break this bond, or are we going to release more energy when we make this bond? They're both pretty similar. Turns out this one's exothermic. And that means that it takes less energy to break this and you release more when you make this. So they're not equalized there, but they're close. All right, so the first step was endothermic. The next one was exothermic, and the final one was exothermic. So how do they all add up? Is this endo greater than the two exos? It turns out the overall reaction is exothermic. So that means that the endothermic, whatever this value is, these two override it. The next two steps override that first endo. Okay, so last year, it seemed like I got a lot, and I think I've seen this before, but more last year for some reason. I got a lot of students trying to do curved arrow mechanisms on the overall reaction. But you don't do the curved arrows on the overall because it's got like, 3 steps to this thing. This is like the overall, just like this. This is like the net overall equation, it's not the mechanism. So you only draw the curved arrows on the mechanisms, like step 1, step 2, and all that. Okay, so I've got a nice mechanism here. And now I'm going to take this mechanism and use it to make my reaction coordinate diagram. So I'll need all these molecules, reactants, intermediates, products. I'll need all that for my diagram. And I'll need to know if the overall reaction is exo or endo. I'll need to know each step's exo or endo, and I need to know the rate determining step. And we'll use all of the above to make our reaction coordinate diagram. So let's do that. I'm taking my mechanism and I'm bringing it over here to have it as a reference on this next panel 5. Before we do that, reaction coordinate diagram, should we take a break or do you want to finish the reaction coordinate diagram first? What do you say? Oh, it's a 2-to-1 vote. Okay, we'll keep going. We'll keep going. It was close, neck and neck. I'm gonna move this over here actually. Oh, here we go. Reaction coordinate diagram. Let's do it. So the reaction coordinate diagram, you have a vertical axis, that's the energy. In our case, we're going to do it as enthalpy. Like delta H enthalpy. Because the real equation is delta G equals delta H minus T delta S. So, but usually at lower temperatures and under normal pressures, atmospheric pressures, your delta G is about the same as delta H. So it's okay to approximate. That's why we always talk about, oh, is that step exothermic or endothermic? Because that's only talking about delta H. If we wanted to be perfectly correct, we should say, is that step not exothermic, but exergonic? I don't know if any of you have heard of that, or it's not endothermic, it's endergonic for the Gibbs free energy. But you'll see with practice, we're not getting all that into the math anyway. So here we go. And along the y-axis or horizontal axis, we have reaction coordinate. It's basically like time. Then at this point, we just start with a line to represent the reactants at some energy level, and we draw the first ones out. So you put on this one, I put my bromide, because that's all I got is my first step of the mechanism. And now I have to decide, should my products of this step, the one up here, you know, where the carbocation is made in the bromide, should that product be the same energy, lower, or higher? What do you think? So this step is endothermic. We got to put energy in, so it's going to be higher in energy. Okay, oh, there we go. Higher in energy because it's endothermic. Now we draw a curve to represent the changes here. So we say that this line is representing like the lowest ground state energy of this bromide reactant, but it can change. It could be like, oh, it gets higher and lower in energy. It's going back and forth. And then when it does lose its bromide, it has to overcome an activation energy to get to that point, to the next reactant. So let's see. There we go. This is our activation energy we have to overcome to become those first intermediates. And this activation energy is for our rate determining step. Remember I said that was the first step was rate determining. And we say, oh, this is transition state 1 up here. The first transition state. Transition state is the highest energy point between reactants and products. So this bromide, it has to like, the way I think of it is, since it's an intramolecular, it's just popping a bromine off. I think of it as like it ran into a solvent molecule, maybe one of the methanols or something, or one of another bromide, and that's what helped it like pop off the bromide. So when it runs into another molecule, it gains a lot of energy and maybe enough to overcome the activation energy and become the product. But If it doesn't collide with something hard enough, then it just comes back. So it's like back and forth, whoop, and then, oh, it hit something hard. Now come over here. Once it's over here, now I have to draw my products, but I also have to draw my next reactant, the methanol there. So I draw the products here, and now I need to think of it as, okay, I've got these products formed, and then this methanol is a solvent in the reaction and a reactant. One of them is gonna float over to react with that first set of products. So I'll draw that in. So I'll say, I'm gonna shrink something down here. Let's put this down here. Okay, you're good. And now I'll be able to draw this. So I've got my methanol. Okay, that's gonna come floating over. And now in the methanol, it's gonna add on to this carbocation, right? Right there, it's gonna add. When it adds on, is that step, did I say it was exothermic or endothermic? I said it was exothermic. So should its line then be higher in energy for the products of this step, the same or lower? It's gotta be lower. If it was higher, it'd be endothermic. If it's the same, then it's neither exo or endo. It is lower. But now when it's lower, it could be here. It can be in line with the first starting material or underneath it, huh? So it's like 1, 2, 3 options. I don't have enough information to tell you where that is right now, and I don't really worry about it. I just say put that line. As long as this line is below, because it's exo, we're all good. So that's where we put our next set of products. We've got the OH. H had the plus charge at this point, remember? So there we go. So we have, again, another activation energy. And another transition state. So next up, what about to finalize the reaction? I need another methanol, right? To deprotonate it. So I have to take and add another methanol under here to show, oh yeah, this is my final step here. I'm going to deprotonate this. Now this next step, is it exo or endo? Did I miss? Oh, I made another mistake. Thank you. CH3, I can't get water off my mind. So the next step is exothermic. Thanks for the correction. Next step is exothermic. So it's not going to be higher. It's not going to be the same. It's got to be lower. So, but should it be lower here, the same as the original bromide, or even lower? So here, I'll write up some possibilities. Should this next one be, you know, should it be here, or here, or here? What's the answer for this question? 1, 2, or 3? Seeing a lot of 3s, and that is the right answer. Good job. Yep, it needs to be lower in energy than the original bromide. Yeah, it has to be lower in energy. So how do I know it has to be lower in energy? Because this has to be delta H less than 0. It's got to be exothermic overall. How do I know it's exothermic overall? I told you, you wouldn't be able to guess that, but in the beginning I said overall reaction is exothermic, so you know the final products have got to be lower than the starting. Okay. Oh, I got to draw in my activation energy. Okay. There we go. So I want you to make sure to do this right. It's easy to make little silly mistakes on this, but notice the following. Notice. One hump per mechanistic step. So we started off with the bromide, and then it became the carbocation and the bromide. And that had a hump, one hump, boop, boop, like that. Then when the methanol adds to that carbocation, gives you this product, that's another hump. And then when the methanol comes and deprotonates that, that's your third hump. So you got a hump for every step of the mechanism. Also, rate determining step activation energy is the largest. Does that make sense that this slow step has the largest activation energy? Yeah, it should, because if it has a large activation energy, it must be slow. It takes a lot of energy. This is much faster. This is much faster. And you can wonder, like, well, wait, if it has this huge activation energy to get to the carbocation, why does it even do it? I think it's just because if it collides with something, it happens to pop off. And if you were to like have an equilibrium constant for just this step, it would be not so good, be like 10 to the -5 or something. But whenever this is made, a methanol could add to it. And then when this is made, another can deprotonate it. So overall, like when it does happen, these steps pull it along. So the first step could be considered not reactant favored, but then the next ones are product favored, and they pull it along. By Le Chatelier's principle, like get rid of this and make more. Okay, so the last thing to do is to draw the transition states to show what they look like. So let's try that. And more examples, practice examples of this. I gave one in the exit question last week, and I'm going to give an entrance question in lab this week. And homework A. Maybe B as well. Let's see. Homework A. Oh no, it's going to be homework B. Sorry. That's right. Here's one. That's a nice one. This one's a E1 reaction. So number 3 from homework 2 and number 4 from homework 2. And I'm pretty sure they both have answer keys too. Let's see. Oh, got some sigma bonding diagram practice. Here's that one. Yeah. Here it is. Yeah. There's the answer key. He's got to hunt for it a little bit. I wrote it out on a Starbucks napkin pre-pandemic. When I guess I could sit at Starbucks by us now and work. I just haven't gone back into that routine. Sometimes it's good to get out of the house and no distractions. Okay, so now the final thing we want to do with this is draw the transition states. This will be on the exam this week, this type of problem, yep. So that's why I'm practicing it, get you good at it. So transition state number 1. I want to move something first. Oh, come on. Oh, let me shrink that. That's weird. Okay. Oh, goodness. Transition state 1. So what we do when we draw transition states is you draw the bonds that are breaking and the bonds that are forming as dots. So in the first step, you have a bond just breaking between the carbon and its bromide. Just like that. And so that's what we think it looks like in the transition state when it goes from being, fully bonded bromide to broken away, fully broken away. It's like bromide's pulling away right there. And there's charges associated with this one. So the bromide starts off with 0 charge and it ends up as a negative charge. So I think it's best to think of it as like a number line. So we have 0, +1, -1, right? So the bromide, it starts off as a charge of 0 and it's becoming -1. So it's in the middle of 0 and -1 in the transition state. So what's its partial charge? Should it be positive or negative? Should be negative, delta negative. It's becoming negative. And then what about the carbon? The carbon started off with 0 charge, had no charge there, and then at the end it's a plus charge. So what is it doing? It's going from 0 to +1. So it's in between 0 and +1. So what should its partial charge be? Delta positive. There we go. Okay, transition state 2. So on this one, we're making that new bond between the carbon and the methanol, oxygen. Okay, so the oxygen, let's see how it's changing. It's going from being no charge to +1. So it's going from 0, 0 to +1. So what should its charge be? Delta positive or delta negative? It's delta positive. Alina had a question about the homework keys. Yeah, the homework key is a homework key I made up last year when I had combined homework A and B, chapters 1 and 2 homework as just a single assignment. This year I decided to break it up because I added a lot of Google slide animations to the chapter 1 material. But when you look at that old key, just hunt around, you'll find your answers for almost all of them. I just don't have time to remake the entire key again. I wish I did, but I don't have so much time. So then next up is the carbon. The carbon started out with a +1 charge and it became 0 charge. So it's going from +1 to 0. It's going in the negative direction. Should I say that it's delta negative? It's easy to mix it up, but that's not what it should. It's going in the negative direction, but it's not delta negative because it's between +1 and 0. It's in between here. It should be partial positive. That carbon, there we go. And we're almost done. Transition state 3. This one's the more complicated one a little bit because it's got bonds forming and bonds breaking. So it starts off with this hydrogen that's breaking, and that's a bond breaking. And then there's a bond forming to a methanol. So we've got, in this case, bond forming, releasing energy. And then over here, we have a bond breaking. Taking energy. This step is overall exothermic, so that means it must be releasing more energy when this forms than it takes to break that one. So let's talk about the partial charges. What changed charge? The oxygen here of the ether, the protonated ether, it went from +1 to 0. So it went from +1 to 0. It's in between +1 and 0. So it's delta what? Delta positive. Then the other oxygen, the methanol oxygen, it came in with 0 charge and it came out with a plus charge. So it went from 0 to +1. It's in between 0 and +1. So it is also delta positive. And we got it. We've done our reaction coordinate diagram.
Based on like atomic size, resonance, and electronegativity. And I just realized I kind of skipped over that outcome. I haven't done that one yet, but I plan on doing it, but I haven't done it yet. But I did say we would do outcomes 1 to 11 on the exam, but we'll skip 8 for now. That won't be on exam 1, outcome 8. So this one we'll get to, I might get to today, but by tomorrow for sure. Last example here. So before I did this reaction coordinate diagram, I said there's 2 concepts we like to use to describe reactions: thermodynamics, the state function, where you're just looking at the state of the reaction, state of the product, and kinetics, the between reactants and products. So let's look at those concepts in this reaction coordinate diagram. So when we talk about the first step being exothermic, or I'm sorry, endothermic, going this reactant's lower in energy than the products. Is that concept thermodynamics or kinetics? That's thermodynamics. When I say this is endothermic, is thermodynamics, just looking at the energy of the reactants, energy of the products. What about the activation energy in this step? Is that thermodynamics or kinetics? That's kinetics. It's what happens between the reactants and the products. What about the transition state? Thermodynamics or kinetics? Kinetics again, because it's the, we're trying, the transition state is just our best guess at what the reactant becomes at the highest energy point before it becomes a product. So it's not, we don't actually have to, we can't isolate this. We just assume it looks something like this because it, it kind of makes sense. The bromine was attached, now it's not, so it's got to be coming off. Okay, and then what about the, when I say overall, it's lower in energy, it's the overall reactions exothermic. Is that thermodynamics or kinetics? Thermodynamics, good job. All right, so for lab today, we'll start off with the pKa quiz, and I'll also give another reaction coordinate diagram for you guys to, for you all to practice and try to let me look at it, and so you're good to go for the exam. And back to our outcomes. So I'm going to skip over 8 for the moment. come back to that. And I'm going to skip electrophile nucleophile for a second. I want to make sure to get some and Lewis-based acids. I'm going to go right to here. I just want to make sure to get to these things that I know are on the exam, the first exam, sooner than later. Here we are. We're going to talk about naming alkanes. So throughout the year, we're going to be learning some nomenclature rules. There's the International Union of Pure and Applied Chemists. They're the ones who set up rules for the rest of the world to follow. And we'll learn some of those. Sorry, I'm having trouble unlocking the iPad. Come on. There we go. Okay. So now we're on panel 6. Cool. So the nomenclature stuff, a lot of teachers, a lot of organic chemistry teachers like to go into a lot of detail on these nomenclature rules and give you some real tricky ones. I'm not so much. And I like you to know the basics and, you know, just kind of with more experience, you get better with it. I understand why the other teachers like to go into nomenclature a lot. It's because they want you to focus in on the structure of the molecule a lot. That helps you then down the line with reactions and things. But I feel like I'd rather you get that focus on the structure experience through spectroscopy. That's why I started with NMR and IR right away. So that's why I'll always have pretty much, I think I'll always have a nomenclature question on an exam, but it won't be too crazy hard or anything. So the way we're going to learn these is we'll have different functional groups. We'll learn that throughout the semesters. We'll start with just alkanes, and then we'll do cycloalkanes, then alcohols, and then alkenes, alkynes. So we'll be learning them slowly. So for this exam 1, we'll have only gone over alkanes. So you'll expect an alkane nomenclature question. All right, so how does this work? So for the alkane nomenclature questions, you first find the longest chain. So let's make up an example, and we'll keep adding to this definition here. So here's a good example to start. 1, 2, 3, and I'll make like a methyl here maybe, and bromide there. Okay, so first you find the longest chain, then you number it. In a manner to give the lowest numbers. So I can number the longest chain here a couple of ways. So hopefully you see the longest chain it doesn't matter really which one I choose here. They're both the same. But so if I number this from left to right, 1, 2, 3, 4, 5, 6, 7, that would be my longest chain. That'd be one way to number it. Another way to number it would be the opposite way. 1, 2, 3, 4, 5, 6, 7. So which numbering system should we use here? Should we use the blue or the green? Let's see. So the blue numbers gave me a 6-methyl. That's how we name the CH3 here, a methyl. It gave me a 6-methyl and a 6-bromo. Yeah, because the bromine and the methyl are on that 6 carbon in blue. If I use the green numbers, I get 2-methyl and 2 bromo. So what looks better? So Annalise, we number the longest chain, and that methyl is off of my longest chain, so it's not part of the numbering for that as like the chain. So what looks better? I kind of said this initially, funny, number longest chain in a manner that gives the lowest number, I should say lowest number for substituents. For substitute. So like the bromine and the methyl are substituents. So which numbering should I use? Lower numbers. So the way you name it then is you put substituents up front alphabetically. Well, alphabet. Am I spelling is that alphabetically spelled right? Yeah, I don't think this has spell check, does it? Alphabetically. Alphabetically? Hey, what happened? Okay. And then and with the parent name. Also have commas between numbers and dashes between numbers and letters. Okay, so here it is. This guy's name is, it's got a 2-methyl, 2-bromo. Who should go first, methyl or bromo? The bromo, because B before M. So this is 2-bromo. I've got a dash between a number and a letter. Then I have to add the methyl information. So I got to do another dash to a 2-methyl. And then I just name the parent name. So this is a 7-carbon alkane. That's the longest chain length. So what do we call the 7-carbon alkanes? Heptane. So this is 2-bromo, 2-methyl heptane. Not bad, right? Let's double check it. There's this program you can download if you want to try. It's it gives you the ability to draw out a long chain like this and then add your groups you want, like the bromide there. See, that's what we're working with, right? And then you can highlight it and have it name it for you. Structure. Generate preferred IUPAC name. Let's do generate traditional. Let's see. Let's do both. So 2-bromo, 2-methyl heptane, or 2-bromo, 2. They're the same this kind. So yeah, not too bad, huh? This program, I like this one. It's called Marvin Sketch. You could try downloading it. They have like, sometimes it gets to be a hassle with the site license agreement, but if you decide to download it, let me know and I'll try to help you. And if you want to practice, they've got like nomenclature apps you can put on your phone that are pretty good. Let's see, nomenclature, alkane, practice. Organic nomenclature for Apple Store. Trying to see. Yeah, I think this one's pretty good. I've played around with this one. Sometimes they get a little more hairy than I do, but they're fun for a little bit. 4.7 out of 5. But here, why don't we just do another one of our own? Okay, let's have you help me make one up. So how many carbons do you want to, well, how many total carbons? Maybe like 10, 12 total carbons? 10 carbons, okay. I'm gonna draw on some boom, boom, and then I'm gonna go 1, 2, 3, 4, 5, 6, 7. I'll just go with that. Okay, so, oh, I didn't switch pages, did I? Thank you, sorry about that. So I went with 10 total here. We've got an alkane, it's got no bromos or anything on it. This one's just straight all carbons and hydrogens. So hopefully you can see the longest chain length would be like 1, 2, 3, 4, 5, 6, 7. I did 7 again. Nah, let's switch that up. Let's make it different. I'll make it 6. 1, 2, 3, 4, 5, 6. Let's say 6 carbons long. Okay, so should I number it this way or should I number it the other way? 1, 2, 3, 4, 5, 6. If I number it the green way, I have a 2-methyl and then a 5. This is the way you do it. 5,5 dimethyl, because there's 2 methyls off of that. 5,5 dimethyl. If I use the blue numbers, I get 2, 2 dimethyl and 5 methyl. Well, actually, I'm doing this sort of wrong, but I'm just trying to figure out the numbering first. So is the numbering, should it be blue or green? The blue, lower numbers. But we're actually not going to use the dimethyl. It's going to be labeled differently. Sorry, I made a mistake initially. This one, you're going to number it. This is how we name this guy. It is 2, 2, 5 trimethyl. Trimethyl hexane. So we got our parent name here. These are our substituents. We've got a dash between a number and a letter and commas here. Not too bad, right? Let's do one more. Oh yeah, I could do this. Okay. There we go. What about this one? So here, I'll just make it more interesting. Okay. What is our longest chain? 1, 2, 3, 4, 5, 6. It's pretty good. 1, 2, 3, 4, 5, 6. Oh, they're the same. Huh? This looks like it's a 6-carbon chain. Another hexane, huh? Maybe I did a hexane. Was the last one hexane? I'll actually, I'm gonna change it up. Let's shorten it up one more. Oh. Okay. So now it's gonna be 1, 2, 3, 4, 5. Yep, or 1, 2, 3, 4, 5. They're the same. So let's just number it along one of them. Should I go 1, 2, 3, 4, 5? Or should I go 1, 2, 3, 4, 5? So let's see. The green one would be a 2, 2, 2 dichloro and a 3 ethyl. See how that's got 2 carbons there? 3 ethyl. And the blue one would be 4, 4 dichloro and 3 ethyl still, huh? So who's winning, blue or green? Green it is. 2, 2 beats out the 2, 4. It's like we're playing poker, but it's low hand poker. So the pair of 2s is lower than the pair of 4s. All right, so let's name this one. So I've got to go with my substituents up front. Should I put the chloral first or the ethyl first? The di, how should I alphabetize it, do you think? Off the di or the C, the chloral? Either way, actually, they both beat E for ethyl, huh? You do 2, 2 because there's a chlorine on carbon 2 and another chlorine on carbon 2. So you got to say, because it could be that the second, see I have 2 chlorines on this molecule. I could have put one of the chlorines on carbon 3. It could have been a 2, 3 dichloro, but they're both on carbon 2, so it's 2, 2. All right, so this one's going to start with the dichloro. 2, 2 dichloro, 3 ethyl, HYL, and 3 ethyl. And then what's our parent name? 5 carbons, pentane. We got it. 2, 2 dichloro, 3 ethyl pentane. Let's double check it. Okay, one more here. Boom. Boom. Chloral's right there. 1 chloral. They're both on carbon 2. Have to delete this extra one. Okay, let us know. Structure. Oh. 2 bromo. What the heck? It's doing all of the molecules. I forgot. I hit the wrong thing. I hit name to structure. Structure to name is what I want. That one. Yes. Okay. 2, 2 dichloro, 3 ethyl pentane. We agree. Okay. So Annalise had a question about this last one here. So it's saying, weren't there only 4 dimethyls? 4? No, I shouldn't have said. I think when I was doing this, I was just trying to get the numbers lower. I kind of did this wrong. I should have put this like, this should have been 2, 5, 5 trimethyl. And then the blue one, I should have put the one that won. It should have been listed as 2, 2, 5 trimethyl. And that would win because it's 2, 2, 2. It's 2 2s and a 5 versus a 2 and 2 5s. So I'm not sure if that answered your question, Annalise, but just ask me in lab if you're still confused. And with that, I'm going to say we pause there. We did a lot today. So let me see for next lecture. 9:22. 8 through 10 above. And but once again, I won't have outcome 8 on exam 1. I'll save that one for exam 2. But I can ask about 9, 10. These are just basic definitions. And 11. And 11, there will be an alkane question like 11 on the exam. And I got a question about the lab being open from 1 to 2 today. Yes, it will. If anybody wants to come in and actually, you know what, the lab's open for the NMR, but you can also do other experiments as well, like just put your goggles on and do the solubility of organic compounds if you want, if you're free. If you are doing that though, I do ask, I forgot to mention this. So if you're going to come into lab and do like wet chemistry out on the bench top where you got to wear your goggles, clean it up a good 10 minutes before 2 o'clock, because then when the people come in at 2 for their lab time, they want to have, you know, not have to wear goggles when they're doing their quizzes and intro stuff.